Okay, today let's talk about section 6.1, composite functions. First, let's discuss why we need the composite function. So, to have a function, you actually have two sets. One is called the domain, and the other one is called the range. So, you have set 1, we call set A, it's a set. And it is mapped to set B, the range of F. Okay, it's like you have a job, you finish it. And once you finish this job, and you can start from your result and do the next job. Okay, so for example, the next job can be done for even bigger class of a set. And it's done under the rule G with the range D. So if you have a input X, you apply the rule F, you get F of X. It is inside B, of course, it is suitable for the second operation G. So you apply the second operation G to this input, Fx, you get G of F of X. So this is the idea of the composite function, because from the beginning to the final thing, we consider you apply two different operations step by step. So step by step application is a composite function. Okay, so this is a composite function because we apply F first and G second. So we write like G circle F of X, and we want to distinguish this composite function with a product of two functions. So we introduce this a small circle notation. Okay, so to make the definition precise, let's write on it here. So given two functions f and g, the composite function denoted by f circle G circle F, G circle F in our order. We read as F composed with we read this G composed with F. G composed with F is defined by the following thing. G composed with F, this is a function, a composite function, evaluated at X. By the definition, it is you first apply F to this X, you get a result, and then you apply G to this result. It is G of F of X. Okay, so this is the definition of the composite function. Okay, so let's see the example. So suppose that fx is 2x squared minus 3, g of x is 4x. Okay, and then let's see. First, find a f circle g evaluated at 1. F circle g, F composed with g evaluated at 1. Then check here, by the definition, you are going to have f of g of 1. Okay, so g of 1, g of x is 4x, so g of 1 is 4, so you get f of 4. So this place, you get the number 4 here. 4 times 1 is 4. And when you get 4 here, you're going to apply f to 4. fx is 2x squared minus 3, so it becomes 2 times 4 squared minus 3. 4 squared is 16. 16 times 2, 32. 32 minus 3, 29. So f composed with g, f circle g of 1 is equal to 29. Right? Second, let's switch the order. We compose g compose f. G compose f. G compose f is g of f of 1. You apply the closer function first. F is closer to 1, so you apply f first. F of 1, you see, when x is 1, 1 square is 2. 1 square is 1, times 2 is 2. 2 minus 3 is negative 1, so it's g of a negative 1. G negative 1 times gx is 4x. G of negative 1 is 4 times negative 1 is equal to negative 4. Okay, so every time when you try to do the evaluation, you actually only do one step evaluation. Here, you just copy this external expression there. You do not apply it because you don't know what is the input. You can only evaluate the internal stuff. The evaluation of the internal stuff depends on this expression of the function, the definition of the function. C, let's see, f composed with f at negative 2. Okay, f compose f, so it's f of negative 2. F negative 2, so you see here, the external function, you copy it. You're going to evaluate the internal function. F negative 2. Negative 2 squared is 4. 2 times 4 is 8, minus 3 is 5. So you have to evaluate f5 to get the final answer. 5 squared is 25. 25 times 2, 50. 50 minus 3, 47. Okay, so this is our first example about the evaluation of composite functions. Okay, so here it seems we can do whatever composition between two functions. The thing is not that simple. We can do this composition f with g, g with f, f with f, or even g with g. It's simply because the domain of f and the domain of g is always the set of all real numbers. So if, for example, you have x, you map x by f to fx, but fx is not in the domain of g, then you cannot go proceed to the second step. Okay, so in order to proceed 2 steps, here it should make sense. So x in the domain of f, and second, fx is in the domain of g. Okay, so that's the condition for the possibility of the composite functions. So let's see. So x is in the domain of f, and fx is in the domain of g, then we can form g of f of x, which is g circle f of x. If either of the condition fails, you cannot form the composite function. Okay. Okay, let's see next. So find the composite function and its domain. Suppose that fx is x squared plus 3x minus 1 and gx is 2x plus 3. Okay, one is a quadratic polynomial, the other one is a linear function. First, find f circle g, f composed with g. What is f composed with g? F composed with g evaluated at x is by definition f of g of x. So we always start from the definition. And the g of x, what is g of x? This is not a number, so you have to use its abstract representation. So it's f of 2x plus 3. F of 2x plus 3. And fx is this, then f of 2x plus 3 means whenever you see x, you're going to use 2x plus 3. So you get a 2x plus 3 squared plus 3. 3 is a number, you copy it. And then you see x. You see x, you copy 2x plus 3 and minus 1. Minus 1 is also a number. Okay? Okay, then you simplify it. Remember that whenever you have a plus b squared, you get a squared plus 2ab plus b squared. Okay, so here's the thing. So a is 2x. 2x squared is a 4x squared. 2ab, 2 times 2x times 3 is 12x, and 3 squared is 9. Here is a 6x plus 9 and minus 1. So you get 4x squared plus 18x. This is 18 minus 1 plus 17. So this is f composed with g. F composed with g. Okay. And second, let's switch the order. G composed with f. G composed with f is g composed with f of x. By definition, is a g of f of x. fx is x squared plus 3x minus 1. So it's a, you always first step copy the external expression and just evaluate the internal function, x squared plus 3x and minus 1. And then you see what is gx. Gx is 2x plus 3. So you're going to replace x by this big expression. So you get 2x, x is x squared plus 3x and minus 1, and plus 3. Here, plus 3. Constant, you always copy. You only change x to be this internal stuff. So we simplify it. It's a 2x squared plus 6x minus 2 plus 3 plus 1. So you see here, in general, let's see here. G compose f is not equal to f compose g. So this is not, we call it commutative. This is not commutative. You cannot change the order. Once you fix it, once it is presented or required in the problem, you cannot change by yourself. Okay, so that's the f composed with g, g composed with f. They are both polynomials. We know that the domain of a polynomials is a set of all real numbers. So the domain of f compose g and g compose f are both the set of all real numbers. Okay, so you don't remove any number. Okay, but let's see another example. In the case, we may remove some point. Okay, let's see another example. Find the domain of f compose G if fx is 1 over x plus 2, gx is 4 over x minus 1. Okay, so you have to satisfy two conditions. Remember, in the first in this part of a discussion, x is in the domain of f, fx is in the domain of G. So x should be in the domain here it's f composed with G, so we're talking about the domain of f compose G is the set that, okay, first x is in the domain of G. X should be applicable to G, and Gx is in the domain of F. Gx is in the domain of F because, check here, we are going to evaluate F at G of X. So G of X should be in the domain of F. Okay, now let's see. What is the domain of G? The domain of G is the set of all real numbers except what? Except G is here. Except x equal to 1. So x cannot be 1. If x is 1, you get a 0 denominator. Okay? So except x is equal to 1. And the domain of F is the set of all real numbers except x is equal to -2. So it means gx cannot be -2. So gx cannot be -2. So let's see what is the value of x when gx is equal to -2. So that's a reason we first set g of x equal to -2, and then we are going to exclude that. Okay, so we solve this. We multiply two sides by x minus 1. So you multiply it out, you get a -2x and plus 2. You move this -2x to the left side, 4 to the right side. So 2x is -2, x is -1. So when x is equal to -1, g of x is -2. So we have to exclude. This point. So what is the domain of f composed with G? So the domain of f composed with G is a set of all real numbers. The set of all real numbers except, first we accept x equal to 1. And second, we accept x equal to -1. Okay, so that is the domain. Except 1, except -1. Okay, so if you want to write it, you can write this way. All the real numbers, x is not equal to -1, and x is not equal to +1. So this is the domain. Okay, so here we do remove some additional points. And this -1 is from this solution of equation. It's not this -2. We don't say x is not equal to negative. We say g of x is not equal to -2. And from here we find the -1. So you cannot just simply say, okay, x is not -1, x is not x is not 1, x is not -2. That is not correct. Okay, this 1 is included, but this -1 is from the solution. Okay, so be careful. Okay, so let's see another example. Example, if fx is 3x minus 4 and gx is 1 over 3x plus 4, show that f composed with g of x is g composed with f of x is equal to x for every x in the domain of f composed with g and g composed with f. Okay, so we mentioned in general these two composite functions are not equal to each other, but for this example, just say for certain pairs you can exchange it, and also they are both equal to x. This is just a special example. Okay, it's not the general case. General case requires something more. Okay, so you are supposed to show something. So you cannot assume it's correct, because before you prove it or before you show it, you don't know if it's right or wrong. So you just compute, and finally you get it. Okay, by the definition, it's f of g of x. External function is always copied, and then you put the internal function here. So f of 1/3 g plus 1/3 x plus 4, and then you apply the f function 3 times x and minus 4. 3 times 1/3 is a 1, so it's x plus 4 minus 4 is x. So what you prove is that, or what you compute is that the f composed g of x is x. Don't assume it at the beginning. You just start from one direction and simplify it and get the other direction. From one side, after simplification, get the other side. That is the proof. Okay, and then let's check the other one. So g composed with f of x. It's a g of f of x. External function, you copy it. F of x is a 3x minus 4. And g of x is 1/3. So you get a 1/3 x. You see x, so you get 3x minus 4. This is x in the example, and plus 4. Constant you always copy. Minus 4 plus 4 is, they cancel. So you get 3x. 3x times 1/3 is x. So what did you do? You computed, and you get g composed with f of x is x. So now you can claim, or you can write down in the long equation. Okay, you can never assume the equality at the beginning. That's a wrong stuff. Okay. So now we have several examples. We know that whenever you have two functions, you can follow some steps and get the composite function. And sometimes you have a very complex function. You want to consider it as a composite function of certain simple functions. So, like decompose a complex function. So, this is the example. Find functions f and g such that f compose g is equal to h with h of x is equal to x squared plus 1 to 50th power. Okay, x squared plus 1 to 50th power. So this is a very complex function. You have the quadratic polynomial, and then you take the 50th power. So how do we decompose it? We actually follow the order of the operation. You see here, when we do this, our first job is to compute x squared plus 1. Once you get this result, you start from x squared plus 1, you apply the 50th power. Okay, so your first job, you evaluate square plus 1. And second job, from here, you get 50th power. Let's switch the order. Here's F, here's G. Because in the problem, they want F composed with G. G is applied first. Okay, so first job, you compute square plus 1. You just check what is your first step. And then from the first step, you apply the second step operation. And this is the correct choice. So we will say, let gx be x squared plus 1, fx be x to 50th power. Here you see here, this whole thing is the input. X squared plus 1 is the input. So we replace this by x, unknown quantity, x to 50th power. Then h is f compose g. Okay, f compose g is of x is f of g of x. You see, f of x squared plus 1 is x squared plus 1 to 50th power. So first you apply g, and then you apply the 50th power. Okay, so that's the decomposition. Okay, so let's see one more decomposition. The decomposition can be the following. Find functions f and g such that f compose g is equal to h if h of x is 1 over x plus 1. Okay, so this is again a two-step operation. The first step, you add 1 to x, and second step, you flip it. So the first step, you add 1 to x, and second step, whenever you finish it, you're going to flip whatever you receive. So you're going to flip it. So f composed with g of x is f of g of x. G of x is x plus 1, so f of x plus 1. And then whenever you have x, you write x plus 1. So it's 1 over x plus 1, it's h of x. Okay, so the decomposition always follows the order of the computation. What is your first step? What is your second step? Okay, so the section 6.1 is very short. It introduces the composite functions of two functions. So you just follow the order of the composite function, you will get the follow the order of the two functions, you will get the composite function. It's like a chain of operations. You get 1 step, 2 step, 3 step, 4 step. Okay, so you can have composite function among two functions, or three functions, or even more functions. It doesn't matter. It's just the number of the steps. Okay. So that is section 6.1. And after section 6.1, we're going to have section 6.2 and one-to-one functions, inverse functions. This is actually the discussion of the case we had. So this one, it's very special. You see here, when you compose f with g with f, they are always equal to x. So what is the idea? So you start from the first operation, you get a g of x, and you apply the second operation, you go back to x. Okay. So what does this mean? This means you first have an x, then you apply f, you get fx, and from f you apply g, you back to x. So it's like back and forth operations. Okay, so this is the idea of the inverse functions. In order to have inverse functions, we must study the one-to-one functions. So what is a one-to-one function? You have a function. Function involves two sets. The domain and the range. If your function always start from does not have a repeated image. For example, if this happens, not this one. If something like this happen, then 2 points will be mapped to the same point. Then this function is not one-to-one. It's not one-to-one. It's like 2-to-1. Okay, 2-to-1. So for the 2-to-1 function, we have a problem. What is a problem? Assume you start from this point. You apply the function f, you reach the circle. But when you and also this second point, second star is also mapped to a circle. But if you want to go from circle back to the stars, you don't know, or at least you have no idea which star do you select. So there's no natural way to name the value for the circle if you want to go backward. Because it has two preimage. We call it preimage. You have two stars. They're both mapped to the circle. But when you go from circle to star, you cannot have two images. One circle can only have one image. So it cannot be defined as a function. Okay, so that's a property. The property we call it one-to-one property. This does not satisfy the property. If we use original solid line instead of a dotted line, we will see that the first star is mapped to first circle, second star is mapped to second circle. You can go backward. Here you go its preimage. Here you go its preimage. Every circle you can find its preimage. Okay? Definition. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. Okay, so this is a definition of a one-to-one. Different input get a different output. What is different input? If x1 is not equal to x2, then it implies fx1 is not equal to fx2. Okay, different input implies different output. And from the graph, you can just see that if there are two arrows pointing to the same point, this is not one-to-one. This case is not one-to-one. If you use this solid line, it becomes one-to-one. Okay? So that's the definition of a one-to-one function. To get a one-to-one function, how do we know if it is one-to-one or not? We have a test called the horizontal line test. The horizontal line test says if every horizontal line intersects the graph of a function f in at most one point, it may or may not intersect the graph. If it intersects the graph, it has one intersection, then f is one-to-one. Okay, so check here. If you have something like this, you draw the horizontal line intersect the graph at 2 points. 2 points, but you know that the horizontal line, the y is fixed, y0. y0, but here you have x1. x1 corresponds to y0. x2 also corresponds to y0. Okay? Then this violates the definition of a one-to-one function. This is not one-to-one. And if you have something like this, I'm sorry, not up. Then for whatever horizontal line, you have at most one intersection. Possibly there's no intersection point if you get too low. Let's assume there's no intersection point. This is also possible. This is one-to-one. Okay, the horizontal line test. Horizontal line test is applied when you know the graph. Okay, when you know the graph, you can apply the horizontal line test. If you don't know the graph, you will not try the horizontal line test. Okay. Okay. Square. Square function is a parabola. Parabola, you see here, whenever you lift this horizontal line a little bit high, you will have two intersection points for one horizontal line. So this is not one-to-one. It is not one-to-one. It's not one-to-one. Of course, we can prove it by the definition, or because 1 is not equal to -1, but 1 squared is equal to -1 squared. So it violates the, it does not satisfy the condition that x1 is not equal to x2, fx1 is not equal to fx2. So that condition implies it is a one-to-one. Here, it does not satisfy the condition, so it's not one-to-one. Okay? And if you have a cube function, you do a little bit computation, you will see the graph, it looks like this. And you can draw whatever horizontal line. There's only one intersection point. So it is one-to-one. This function is a one-to-one function. Okay, and this function, remember, when we have such a graph, if you move from left to right, you're rising up. You're rising up. This is called increasing. If you're going down, it's decreasing. So we have a theorem. Part 1, f is increasing on an interval I, then f is one-to-one on I. So like this, if it's increasing, so it's a one-to-one. B, f is decreasing on an interval I, then f is one-to-one on I. Decreasing, you can consider fx as a negative x cubed. It's like this. So it's also one-to-one. So increasing function one-to-one, decreasing function is also one-to-one. Okay, so that's one property of functions. We talk about functions. And let's see why we are interested in the one-to-one function. It's because of the inverse function. Remember that we go from star to circle, and we want to go back from circle to star. The go back process, we call it the inverse. Okay, so the definition. Suppose that f is a one-to-one function. Only one-to-one function can be discussed for the inverse functions. Then to each x in the domain of f, there is exactly one y in the range and this part up to this part, it's a definition of function. So for one x in the domain, there's exactly one point in the range. This is a function. And to each y in the range of f, there is exactly one x in the domain. This is one-to-one. This statement is a one-to-one. This statement is a definition of function. For x, there is a y. For y, there is x. Go back, it's a one-to-one. Then the correspondence from the range from y to x, the range of f back to the domain of f is called the inverse function of f. The symbol f-1, f-1, we consider it like f inverse, is used to denote the inverse of f. Okay, so that's the definition of the inverse function. Okay, this is definition inverse function. So let's see the example. Let's see the example. Let's see the example. So first, one-to-one function. One-to-one function. We can use pairs to represent one-to-one function. -3, -27, and -2, -8, -1, -1, and 0, 0, 1, 1, 2, 8, 3, 27. Okay, so this is a one-to-one function. For one input, you have an output. One x, you have one y. Because we don't have a lot of values, so we can list them. Then what is the inverse function? Its inverse function, f inverse, is what? You just get the output of the origin function as input. So -27, it becomes input for f inverse. Then the -3 becomes output. Here the same thing. -8 becomes input. -2 becomes output. -1 becomes input. The other -1 becomes output. You actually switch them. And here 0, 0, you also switch them. 1, 1, you switch. And 2, 8, you switch, you get 8, 2. 3, 27, you get a 27, 3. Okay, so that's the meaning of this inverse. From the inverse function, you can see that the domain of f, this is domain of f, becomes the range of f inverse. And the range of f here, it becomes a domain of f inverse. They really exchange the domain and the range. Okay, we exchange it. You go from here to circle. Start from you go from star to circle, and by the inverse function, you go back to the star. So that's the way for us to verify if two functions are inverse to each other, because you apply f to x. So you apply f to x, you get this circle, and then you apply the inverse function, you back to x. So that's the property. So f inverse composed with f is like this. And similar thing, you start from the circle, move to the left, you get the star. Start from circle, you get the star, and then apply f, you go back to the circle. So and the difference is that the star comes from this part. The star comes from the domain of f. And this circle comes from the domain of f inverse. Even though we use the same symbol to represent, we both use x, but one x is from domain f, the other x is from domain f inverse. Okay, so keep this in mind. We can verify by the example. Verify gx equal to x cubed, and g inverse of x is cube root of x inverse to each other. Okay, so g and it's an inverse function. So how do we verify it? To verify it, we just verify these two situations. This is the verification property. So we are going to compose G inverse and G of x. G inverse, copy it, it's external. G of x, what is G of x? X cubed. Okay, and you apply G inverse to x cubed, you get cube root of x cubed. Cube root of x cubed is x. So you get G inverse composed with G is x. And the other one, G composed with G inverse, copy the external function. G inverse is cube root of x. And then you get cube root of x and then cubed. You also cancel the cube root with the cube, you get x. And by these two computation, we verify that they are inverse functions. Okay, so just do the composite function, you will get the inverse. Okay, and let's see another one example. Verify that fx equal to 1 over x squared has its inverse f inverse of x equal to 1 over x plus 1. Okay, we verify this function has inverse function like this. So how do we verify it? Do the composite computation. So you always first copy the external function, apply the internal function, and then you apply the external function to this internal expression. So 1 over whatever stuff here. 1 over means you flip twice, you're back to x minus 1. You flip twice, you're back to the original, and the plus 1. Minus 1 plus 1 is x. Okay, so you verify that f inverse of fx is x. But be careful here, this x cannot be positive 1. X cannot be positive 1, because when x is positive 1, this part is undefined. Okay, so x cannot be positive 1. And if we verify the other part, the other identity, f of f inverse, what is f inverse? 1 over x plus 1. So f of 1 over x and plus 1. And then you apply f to this expression. This expression is x here, so you 1 over x, this is big X, and minus 1. Plus 1 minus 1 is 0. So you get 1 over 1 over x. 1 over 1 over x is x. Okay, so we verify that the composite function f composed with f inverse of x is equal to x. But here, this x is not equal to 0, because this gave us a restriction. X cannot be 0. Here, x cannot be 1. So you see that those two identities, even though you have two identities, they are not they are not identical. They're both x, but here x is not 1. Here x is not 0. They have different domain. Okay, so we will stop here for this moment, and the next time, we will continue the discussion about of these inverse functions, and we will study the graph of the inverse functions from the graph of the original function. Okay, we stop here. Thank you.